The other question I thought we'd do is question 21 from the sample pack. Some of the eagle-eyed might have noticed that in the sample pack there is no question 20. That is merely a mistake. That's the diagram attached to question 1. It says a trolley of mass capital M is attached to ground by a spring, okay, K, as shown in figure 21. The trolley has a pendulum of length L and mass M attached to it. Assume that the wheels of the trolley and the cord of the pendulum are massed. So there are a couple of wheels here, okay, and ground here. And it says, part A, find the equations of motion for free oscillation of all, not necessarily small, thetas. Okay, so the process here is to use Lagrange's equation, because we've got a pendulum, and the pendulum, by definition, is non-linear if we don't assume small angles. So the first step is to calculate the kinetic and potential energies. Now, to calculate the kinetic energy of the pendulum, I need to use my xy coordinates. So if I set this to be, well, my x, I've already set is over there. My y is in this direction. So x, y, this is of the bob. It's quite clearly going to be x plus L. Then we've got this distance here, which is sine of theta. And then we've got y is going to be minus L cosine of theta. So I've set my datum. This is my x starting point, and this is my y starting point. Obviously, the mass will have moved out a certain distance x, okay, and obviously my y, this is going to be in minus direction, and it's L cosine of theta. And so, to find my velocities, I differentiate this, x dot, y dot, that's of the bob, and so I'm going to have here x dot plus L theta dot cosine of theta. There's my chain rule, and here I've got L theta dot sine of theta. The minus sign disappears because the differential of cosine is minus sine. So we've got the velocities of the pendulum. Obviously the velocity of the mass quite simply is x dot. And so we can write out my kinetic energy. T is 1/2 big M x dot squared plus 1/2 little m x dot b squared plus 1/2 little m y dot b squared. So let's plug the values in for x, b and y, b. We've got x dot plus L theta dot cosine theta squared plus 1/2 m L theta dot sine theta squared. And going through the motions, mx double dot and mx dot plus 1/2 m. We've got x dot squared plus 2 L x dot theta dot cosine theta plus L squared theta dot squared cosine squared theta plus, I'm going to take my 1/2 m over this side as well, L squared theta dot squared sine squared theta. Now obviously cosine squared plus sine squared is 1, so that term disappears. And so if I take my 1/2 out over here, I've got an m times x dot squared, a little m times x dot squared, so that's going to be 1/2 m plus m x dot squared. Okay, and like I said, I'll take the 1/2 out of everything. So that's that half taken into account. And we've got plus this term, plus 2L, sorry, I've got to take this n into account, m L x dot cosine square, cosine theta, plus m L squared theta dot squared. That's my t. Okay. Don't worry about that. So like I said, I've got a half term here and here, so I've taken that out of the equation. We've got an m times by x dot squared and little m times by x dot squared. So I can do m plus m, okay, times by x dot squared. Okay, and then like I said, I've taken the half out, but I need to include the m in each of those terms. So I've got my 2 m L x dot theta dot cosine of theta, which is there, plus m times by this term, because cosine squared and sine squared of theta, add them together and you end up getting 1. So that can disappear. We end up with just one of these terms, L squared theta dot squared times by m. So there's my t. V is a bit easier. It's simply the spring force, 1/2 kx squared, okay, plus mgh for the bob, which is minus mg L cosine of phi. It's a minus sign because this h distance up here is minus. So there's my v. So if I set Q1 to be x, Q2 to be theta, and big Q1 is 0, big Q2 is 0, there's no forces being applied, L is T minus V. So we have 1/2 Okay, so there's my L term. L is t minus v, so I've taken my t, I've separated it out into nicer terms. Okay, so it's not grouped up like it is here. I've distributed the half out throughout those terms. So the half times 2 is 1, so that's where that 2 disappeared to. And obviously here I need to put a half in front of this term. And then my v term obviously is minus v, so that turns into a minus, that turns into a plus. So there's my L. And so for Q1, okay, that's dl over dx dot. We've got m plus m times by x dot, which is this term. The other one I need to deal with is this one here, which just becomes plus ml theta dot cosine of theta. If I take the time derivative of this term, so that's d by dt plus ml theta double dot cosine of theta. But because I've got a theta in here, theta dot varies with time, but so does theta. So I need to use the product rule over here. So we end up with a minus ml theta dot sine of theta dot squared. So that's theta dot. So like I said, here's my partial derivative with respect to x dot. So the only term I need to consider is this one and this one. There's no x dot in either of those terms, so we can forget about them. They're constants when I take the partial derivative of L with respect to x dot. So I get these two terms. I then have to take the time derivative of this term. Okay, well that's quite clearly just going to be the same thing with x double dot. Okay, but here we've got two things that vary with time, theta dot and theta. And so we need to use the product rule. So we've got ml theta double dot times by cosine of theta. Okay, so then I have to take the derivative of this with respect to time and multiply it by what I've got out the front here. So I end up with ml theta dot squared times by sine of theta. Partial derivative of L with respect to x, the only term I need to consider is this one over here. So that just becomes minus k x. So I could write out my Lagrange's equation for this. That's this term minus this term. So we've got a equals 0. So 0 equals m plus m x double dot plus ml theta double dot cosine of theta minus ml squared theta dot squared sine of theta minus this term plus kx. I'll repeat the process for Q2. So let me bring L back into the picture so you can see what we're doing. Partial derivative of L with respect to theta dot, well there's one here. There's one here, and that's the only terms, two terms we need to take into account. And so we have ml x dot cosine of theta. And then this term, obviously got theta dot squared. The 2 comes down, making that a 1. So we have m l squared theta dot. Time derivative time. Again, product rule, x double dot cosine of theta minus ml x dot theta dot sine of theta plus L squared theta double dot. Yes?
In the first one, you did dl by dx.
Yep.
The second one, you did dl by dt.
Because I said that Q1 is x,
Okay.
Q2 is theta. You've got to deal with each of the degrees of freedom. And I've got 2 degrees of freedom. One is x, and the other one is theta. Okay, so that's why. And then I've got dl over d theta. Well, the only term, there's 2 terms that have got theta in. This is one of them. And this, sorry, L. This is one of them. And this is the other one. Okay, so I need to deal with both of them with respect to, to partial derivative of L, which is this one, with respect to theta. So this becomes minus ml x dot theta dot sine of theta. And then this one also becomes minus mgl sine of theta. So plugging them into Lagrange's equations, we've got 0 equals ml x double dot cosine of theta minus ml x dot theta dot sine of theta, which is this term, plus ml squared theta double dot, plus this term, ml x dot theta dot sine of theta, plus mgl sine of theta. Now notice that this term and this term are the same. One's a minus, one's a plus. They disappear. And we end up with 0 is ml x dot double dot cosine of theta plus ml squared theta double dot plus mgl sine of theta. So there's my equation for theta. And that was my equation for x. So that's part A. Wait for you to finish. We can quickly do part B before the end. Part B asks, what would the equations be for small values of theta? So now we can assume small angles. What would the equations be? Well, there's a couple of ways we can solve this. Okay, the long way is to start from the beginning again, assuming small angles. The shorter way is to take these equations and apply small angle approximations. But there's actually one more approximation we can apply. Small angles means that sine of theta is equal to theta. Cosine of theta is equal to 1. And the other thing we're going to say is that if theta is small, then the velocity is likely to be very small. And so the velocity, the square of something very, very small is even smaller, teeny weeny. So we're not going to worry about theta dot squared. That's equal to 0. So those are the approximations I'm making. Now if we take the first equation, which is up here, okay, we've got m plus m x double dot, so we don't worry about that one. Here we've got a cosine of theta. Well, we know that equals 1, so we've got plus ml theta double dot. Here we've got a sine of theta. Well, we know that equals theta, but we're neglecting theta dot squared. So that term just appears, plus kx equals 0. So that's the first equation. And the second equation, down here, cosine of theta equals 1. So we have ml x double dot plus ml squared theta double dot. Okay, sine of theta equals theta plus mgl theta equals 0. So there's my simplified equations, and I can actually write this in matrix form because it's now a linear system. So my mass matrix looks like this, m plus m, and then we've got this term times by x double dot, so that's ml here. We've got ml times by theta double dot, and ml squared times by theta double dot. So there's my mass matrix, x double dot, theta double dot, plus my stiffness matrix where I've got k times x, 0 times by theta, and here I've got 0 times by x, and mgl times by theta. Job done. So it becomes a linear system that you can write in matrix form.